Happy afternoon session, everybody. Almost done with the first day. Let's go ahead and get started. So my name is Reath, and I lead the NoSQL infrastructure team. And with me today is my colleague, Lindsey Zurovchak. And today we'll be talking about how we modernized our Cassandra backup system using Medusa, which is a backup utility originally created by Spotify and the Last Pickle / DataStax. But before we go into that, we'll talk a little bit about who is Bloomberg. Bloomberg is a technology company that provides financial data primarily through software known as the Bloomberg Terminal. The terminal has more than 350,000 subscribers, offers different financial analytics tools, which we call functions, finance professionals around the globe who use the data and news we provide every day to do their jobs. We have over 25,000 employees in 70 countries, more than 9,000 of whom are engineers. Many of our engineers are active members of open source communities as both users and contributors, with some who serve as PMC members or hold governance roles. Bloomberg has transitioned over the last 2 decades into becoming an open source first company. We use hundreds of our open source projects in our products and infrastructure. And a little bit about the NoSQL infrastructure team at Bloomberg. We offer Cassandra as a managed service to engineers at Bloomberg. Our goal is to make it easy for engineers at Bloomberg to use Cassandra to power their applications without needing to understand the complexities of managing a large-scale distributed database. We started in 2017, and we've been going ever since. A little bit about the managed Cassandra platform at Bloomberg. Right now, it's just about over 3 petabytes of data, nearing 4,000 Cassandra nodes, broken into about 300 Cassandra clusters. So maintaining a backup solution is not trivial regardless of your scale, but at this size, it's critical that any solution we build is both fully automated and efficient in terms of storage and network bandwidth. So before we dive too deep into how we back up Cassandra, we're first going to discuss why you should back up Cassandra at all. After all, Cassandra is really good at maintaining uptime in the event of database failures. So while it's true that backup is generally not needed in the event of a single node or even a data center failure, there's still really good reason to back up Cassandra. First and foremost, backups can help protect against human error. Cassandra will happily replicate every command that you give it, including the ones that you might not mean to. While it might be difficult to write a script which accidentally deletes all of your data, it's not impossible. Especially when operating a platform team, you need to be a bit paranoid about what commands your users might send. If you have backups available, sleep easier at night knowing that even if a user completely corrupts their database, there's still a way to bring them back to a good state. Second, backups help protect against data corruption or data loss due to infrastructure issues, including disk failure, bit rot, etc. And while it's unlikely that with high enough replication factor, you can experience widespread data loss, it's not impossible. And if you do, you'll be happy that you have a backup. And finally, backing up your Cassandra database helps improve the liquidity of data in your systems. With backup and restore tooling, you can easily clone clusters, which you can use to test changes like Cassandra upgrades, configuration changes, or even application level improvements. Now, I don't think I have to work too hard to convince this room that Cassandra backups are necessary. But you might have some difficulty getting your business to buy in and spend the money necessary to back up Cassandra. After all, it's a lot of data and might be expensive to back up. So here's a few things that you could use to help convince your business that backups are necessary. So in addition to the operational resiliency benefits of backups, there are many business requirements that backups help satisfy, such as audit requirements, where you might need to be able to see the state of a database as of time. Regulatory compliance, where different regulations dictate how databases are meant to be operated. And then finally, in the event of major disasters such as natural disasters, ransomware attacks, or security breaches, backup can be used to restore business as soon as possible and get back to service. And so now that you're all convinced that you should back up Cassandra at all, let's talk about what Cassandra offers out of the box and how you can use these tools to help back up your database. From a backup perspective, Cassandra offers local backups through a number of different mechanisms. The first is by running node snapshot. Running this command on a node will flush mem tables to disk and create hard links to the SS tables that are created. If an SS table is deleted by the compaction process, or if you accidentally run RM on it, the file contents will be retained in the backup location. The second thing Cassandra offers is auto snapshot. This is enabled by default and will create a snapshot on disk with truncate or drop command is issued to the database. This way, you can guard against one of the most common user errors, where they just drop their data and say, hey, my data's gone. Can you please restore it? Finally, Cassandra offers incremental backups. A hard link is created to a file in the backup location when an SS table is created. Similar to NoTool snapshot, if you remove this file, the original SS table file, if you delete it, the contents will still be referenced in the backup location. So now that you have a backup, how do you actually restore your data? To do that, Cassandra also offers a couple of different approaches. So if you're looking to do an in-place restore, you can just move the data back into the live data directory of your Cassandra node and use NoTool refresh to tell it or you can restart your Cassandra node. Or if you want to restore to a new cluster, you can use the SS table loader, take the data files, and stream them to a new Cassandra cluster. And so while these tools are a great foundation to build upon, they're a bit lacking for a large-scale production deployment. First, as all of these tools are node local, you must build your own orchestration layer to perform these operations across a cluster, or you'll have an incredibly manual backup. Second, these node local backups are not resilient to many of the different failure modes which we've discussed already. If the disk become corrupted, then your local backups probably too, you won't be able to restore them. Finally, since the backups are created locally, there will be some storage costs that you need to pay to keep them around. If you're looking to keep many years worth of backups, you might need a much larger disk than you typically need for a Cassandra node, which is going to be significantly more expensive than moving to backup data to a lower cost, higher latency storage solution. So before we get into how we implemented backup at Bloomberg, we'll talk a little bit about how we actually deploy Cassandra at Bloomberg. Give you some context. We run Cassandra on bare metal machines as containerized processes in Bloomberg managed data centers. Typically, we have a few nodes from different clusters running on each machine. To manage these containers, we leverage a container agent that runs as a sidecar on the machine. We also have a Cassandra-specific sidecar running on each machine, which gives us access to node utilities like NoTool over HTTP. When we start a Cassandra container, the container agent will reach out to a metadata service, which manages information like what clusters run on this host and how are these nodes configured, and the specification for each container. The container specification includes information like which ports to use, the data file paths that mount volumes into the container so that the processes can actually access the SS table on disk. In addition to Cassandra containers, the container agent also manages what we call init containers, which are short-lived containers that run before a Cassandra container is started. Init containers support things like creating configuration files and directories, configuring users and permissions, setting up other aspects of the environment before the Cassandra process is started. And so now that you know a little bit about how we deploy Cassandra, we'll talk about our previous implementation of backups and why it left us wanting more. So our initial backup solution was using volume level backups. In this system, an infrastructure team managed taking the backups of volumes on disk and offloading them to a remote storage solution. In this system, we had a nightly job which calls an orchestration service, and this service was responsible for talking to our metadata service to look up the nodes on which a given cluster was hosted and call out to our Cassandra sidecar in parallel to create the backup. Cassandra sidecar would then call out to NoTool to run snapshot, which would tell Cassandra to create the local snapshot on disk. And then the Cassandra sidecar would move the backup to the location on disk, which was monitored by the backup infrastructure. On a schedule, the backup agent provided by the volume backup team would then copy the data out to a remote storage solution. And so for us, this system was pretty nice. First, it let us have a very minimal system. All we really needed to do was take a snapshot on disk and move it to the right location, and then the infrastructure team managed the rest of it. However, there was a number of disadvantages of this system. First, the restores had to be done in place back to the machine from which the backup was taken. This doesn't really match well with Cassandra's dynamic architecture, and at Bloomberg, we move Cassandra nodes very often to allow us to do things like rebalancing, replacing nodes in case of failure, etc. And so a backup that was taken on a given machine might actually be needed on another machine to perform a restore. In addition, the restore process was very manual. A ticket would have to be placed into the infrastructure team, would then move the data back onto the machine, and then an operator from our team would have to go and tell Cassandra to reload the data back into the system. Third, there was lack of observability. It was really difficult for us to tell when the snapshot was actually moved off of disk so we could clean it up. And finally, the cost of this solution was very high. As the volume level backup system had no insight into the topology of a Cassandra cluster, it could not deduplicate data from replicas. Additionally, this required an entirely custom tooling from our team, did not allow us to take advantage of any existing open source solutions. So after a while of living with this old system, we decided that we needed to revisit our options and help solve some of the issues we faced. I'm going to hand it over to Lindsey to talk about the new system that we created.
Everyone hear me? So when exploring a new backup solution, we considered a few options. We could leverage the existing Cassandra tools such as NodeTool Snapshot and SS Table Loader as parts backing up key spaces locally like we were doing with our previous system, but we would have to build out that remote storage connection logic ourselves. This would have required a lot of custom code, and we were convinced we were not the first people to fix this load. The other option we explored was to add in that missing remote backup functionality directly into Cassandra or into Cassandra's sidecar to fill the gaps not only for ourselves, but for everyone. This was obviously our most desired solution, but it required taking more time than we could afford to get the solution to a stable place to be included in the new Cassandra version. So we decided this is a great long-term plan, but we still needed a short-term solution to get backups working. The third option we explored was Medusa, which is a Cassandra backup system that was originally built by Last Pickle, Spotify, and is open source. So it was pretty attractive to us to find something that was made specifically for Cassandra that was also supported by the community. Ultimately, it should be no surprise, given the title of this talk, that we chose Medusa for this solution. So why do we choose Medusa? Some of the pros are that, as I said, it's built specifically for Cassandra and therefore understands Cassandra architecture and concepts such as NodeTool, SS tables, tokens, and snapshots. It fills in that remote storage gap as it works with our S3 compatible storage right out of the box. It supports both full and differential backups, as well as cleanup functionality, all of which I'll touch on in the next few slides. And it supports restoring to a node, the same cluster, and a new cluster with both the same or different topology. So that all sounded pretty great. There were still a few things that we needed to iron out. For starters, Medusa runs either as a command line process or as a gRPC service to support Kubernetes-based clusters. But we don't run on Kubernetes, so if we wanted to use Medusa as a service, we would have had to create an HTTP wrapper ourselves. Additionally, we liked that it had built-in orchestration capability, but we were hesitant on using this since it connects to nodes using parallel SSH. We wanted to ensure that only our Cassandra and container agent ports were accessible for these machines, and we weren't keen on managing SSH keys for thousands of nodes. So we decided the solution would be to run the Medusa CLI as a sidecar-like process in Docker. That way we could work towards building this logic either into Cassandra internal or Cassandra sidecar and not have to completely alter our strategy to use that functionality when available. Additionally, rather than using the built-in orchestrator, we chose to build out our existing orchestration pipeline that manages our containerized Cassandra instances to support these Medusa processes, or more generally to support these short-lived command-style processes. So what does this orchestration pipeline look like? So when a backup request is made, our orchestrator pings our metadata service to get some information about which nodes are part of the cluster and calls out to the container agent on each machine. The container agent then fetches some Medusa config information, such as the NodeTool port, the remote storage information, and other environment variables from our metadata service, and spins up a Docker container that runs the Medusa CLI. The Medusa container can then communicate with the local Cassandra container, as well as the remote storage. This allows us to leverage our existing orchestration with minimal updates, run Medusa to back up individual nodes rather than using the Medusa orchestrator machine. As part of this initiative, we introduced something called a utility container, which, like an init container, is a short-lived process, but is designed to run while the service container is running instead of before it. And by modifying our pipeline to support short-lived processes, this also allows us to run other types of command containers, such as NodeTool or CQLSH. So when we run the Medusa CLI, what happens? Medusa requires a configuration file to determine how to run. And some of these values can be defined and overridden by environment variables at runtime, but for the most part, these values have to be defined in the file. And this was initially a challenge for us when trying to use the CLI across many clusters. So we create this file at runtime in the Docker container with an entry point script that fills values from our environment variables that we populate from our metadata service. Now, a lot of Medusa's magic comes from being able to read the Cassandra YAML file, which is Cassandra's configuration file, to find data file paths and other information about the cluster. So we needed to either mount this file or create a copy of it within the container so Medusa can access the information. And since we're using our own orchestrator, the command here is backup or backup cluster. This allows Medusa to reach out to the Cassandra process running on the local machine. So once the entry point script is executed and the Medusa container starts, Medusa calls node to a snapshot, which triggers the Cassandra to create copies of the SS table files in the snapshots directory. And because of the Cassandra YAML file, Medusa knows exactly where to look for these snapshot files. It then uploads these files to your configured remote storage, and voila. So what exactly does this data look like in the remote storage? Well, that depends if you've configured Medusa to take full or different. In a full backup, Medusa will upload all files in snapshot, regardless of what's already been uploaded in previous backups. So if we take a look at the example here for a single node in our remote storage bucket, we see that each backup will have its own manifest file that references its own version of the SS table files. After the first backup is complete, we see SS table 1 has been uploaded. Some time passes, backup 2 completes. We see that during this backup, it uploaded the new file SS table 2, as well as its own copy of SS table 1. And the same for backup 3. This means that across these 3 backups, there's 3 of the total 6 files that are duplicates. So if for some reason some of your backup files are corrupted, you might want to do a full backup since you can't be sure which files are actually accessible. But if not, you can see how this might start to take up a lot of unnecessary storage, especially since this is only for one node in a cluster of potentially 10 or hundreds of nodes. So if we want to look to limit these copies, we can leverage what's called. Now, in this case, each backup has its own manifest that will reference the SS table, same as before. Only now all SS tables that exist under the same storage path, irrespective of the backup. Which means that once the snapshot is taken, Medusa will check if the SS table file already exists in the storage path and will not re-upload it if it does. Now, this is possible because we know SS table files are mutable and no new data is being added to them. Therefore, we can be sure that if the file is present, we know that it does not need to be re-uploaded. We only need to upload the SS table. Therefore, differential backups not only limit storage space and costs, but also prevent unnecessary streaming and decrease the time it takes to backup. And this is one of the biggest benefits of the Medusa approach, as our goal was to implement these differential backups in order to optimize the storage. So aside from any ad hoc situations, we currently run differential backups for all of our clusters. So that's great, we have a backup. What happens when you have to make use of it? So our pipeline currently only supports restoring to a new cluster with the same topology. We took this initial approach in order to follow the immutable infrastructure model so that existing clusters are not affected during restoration. This allows us as operators to easily test our restore process without disruption, but it also gives the user the flexibility to decide how to handle the data written between the most recent backup and now. So restores are effectively handled as new clusters. What does this look like? Our orchestrator will create a record in our metadata service, indicating on what machines a given cluster should live. And when doing this, we also pass the ID of the backup from which we want to restore. The orchestrator then reaches out to the container agent to start the Cassandra service on the machine. Now, the Cassandra service container spec includes an init container, which, as we mentioned earlier, is a short-lived container process that runs before the start of the service container. So this init container creates the initial configuration for Cassandra, and when an ID for a backup is included, it will perform a restore. The init container runs a Python script that uses the backup manifest to calculate which node it's supposed to be based on the topology information. And with this information, the init container can then leverage Medusa to download the data and backup in the remote storage, move them to the correct data directory, configure the initial token for the node, and start Cassandra. So we have the ability to take a backup and to restore it to the cluster, but that's still only half the battle. Now I'll pass it back to Isaac, who will talk about the maintenance of these backups.
And we'll talk about everyone's favorite topic, KTLO. And so in terms of backups, we break this into two categories. One is retention policies, and the other is maintaining the integrity of. So the cost of storing all of this data can be very expensive, not only in terms of dollars, but also in terms of physical data center space and power utilization. We need to ensure that we're only ever storing backups that we need, and this is where retention policies come in. At first, you might just think that a bucket level TTL could help you purge the data when you no longer need it. But because we use differential backups, we cannot simply use a bucket level TTL, as the nested table, which is referenced in multiple differential backups, can expire, leaving you with an incomplete data set. So fortunately, Medusa ships with functionality which is called purge, which helps keep your backup costs minimized while taking into account which nested tables are still needed. Medusa purge takes in either a number of backups to retain in the remote storage, or a time to live for. When purge runs, we'll look at all of the backup manifests and delete each manifest which is older than either the max backup age or is not part of the newest N backups. After deleting these manifests, Medusa will take a look at the essence tables which are stored in remote storage and delete any essence table which is not referenced by an active backup. Through this, Medusa will delete only the essence tables which are not needed by an active backup and ensure that our storage footprint for backups does not grow too large. So out of the box, Medusa Purge requires that we run it as a CLI for every Cassandra node. And as you might imagine, for thousands of Cassandra nodes, this can lead to a lot of toil. Instead, we have an automated purge job which runs on the completion of a given backup to ensure that the data is expired at the right time. Now moving on to ensuring backup data integrity. Just because you uploaded a backup in the past does not guarantee that you can restore it in the future. And so verifying that we backed up can be restored is important to ensuring that we can sleep well at night. To make sure that we can identify these cases proactively, we need to periodically check that backup is still restorable. So today, Medusa offers functionality called Verify, which runs MD5 hashes for the essence tables in the remote storage to ensure that what was uploaded is still there. However, in the future, we're looking to periodically restore our databases and run correctness checks on that data to ensure that the data is still restorable and that we're exercising our restore process. So speaking of the future, I'll talk about some of the future work that we are going to have for our backup restore. First, we'll start with some Medusa improvements that we've identified that we'd like to feedback. This includes improving the speed with which MD5 hash calculations are performed to verify data integrity when performing a differential backup. On really dense nodes, this can take a very long time and ends up being like the bulk of the time spent doing a differential backup. In addition to this, there are a few quality of life bugs that we've identified in Medusa that we'd like to fix and contribute back as well. Beyond the Medusa improvements, we'd like to update our systems for point-in-time restore. Right now, a restore can only be brought back to the time at which a snapshot was taken, but by using commit log archiving and incremental backups, we feel like we could get a full point-in-time restore solution. Beyond point-in-time restores, we'd like to work on improving the storage efficiency of Medusa backups. Right now, Medusa stores the data for every replica. We would like to see if we can improve the storage efficiency of backups by reducing the number of redundant replicas which we back up. And finally, while we're pretty happy with what Medusa has been able to offer today, I think we can all agree that removing additional dependencies is better than adding them. And to that end, we're going to explore whether or not we can have a Cassandra native solution, either in process or via sidecar, which can manage backups and restore supports. And so with that, we'll take questions. I'll go in the front first. Light blue shirt in the front first. Yes, yes.
I mean, we Morgan Chase, we use cookies. Did you look at that at all? Or is there any way you can compare the master?
We didn't. I've never heard of Cohesity. Is that like a vendor provided solution?
It's a vendor solution.
Yeah. I would say that definitely at Bloomberg we look primarily at open source solutions pretty much exclusively, and so that's why we didn't consider that. All the way in the back.
So at Blizzard, we love Medusa, we use it a lot. Tell me about your retention. How did you come to where you decided to have your retentions? We went through a little bit of back and forth between the cost of certain bucket policies where it would be cheaper because you don't access it that often. So we kept them longer, and that playing into the calculus of how much you're storing.
I don't know how much I can speak to, but I can speak to, so at Bloomberg, we're basically told how long to retain things for. So for better or for worse, we don't have to make that decision, but also there are times when, it's being recorded, there are times when I'm like, I think we could do better than that, but at the end of the day, policy is policy, so we have to implement it. Jordan?
Yeah, so I was curious, when you bring up point in time store, have you all felt you have the need ever for single key or more targeted restore, or when you look at restore,
We've definitely had clients ask us for that, but then when we come back to them and say, what's the use case, it's mostly for an ETL copy type workload as opposed to, oh, I just need to restore the single key from a disaster recovery perspective. I would love to offer that for just to solve the user needs, but it just hasn't been that big of a priority.
Same for this is the reason I asked.
Yeah.
We get those. We have this thing called refreshes where we take the prod data and test with the restore. That's kind of weird. But then some people are like, I just want to refresh these 10 keys. The other one is user data loss, user bug. We actually just these 5 keys.
Yeah, we've definitely had people ask for that, and it's kind of just sorry.
Yeah, good, but prioritization.
Yeah.
Well, I was just curious.
Yeah.
If you currently don't have PITR, time restore, what's your current RPO and RTO?
I don't think I'm allowed. I'm going to err on the side if I don't think I'm allowed to talk about that. But
do you have any requirements from your customers?
We do have requirements.
RPO and RTO.
Yes. And more importantly, I talked about regulations at the beginning. There are definitely new regulations going into place that are trying to dictate that as well. So there's no better motivator than
Did you ever use backup on production and restore?
Have I ever had to restore a cluster on production?
Yeah.
Fortunately, yes.
Was it a user error or a hardware problem?
It was a user error.
Cassandra bug.
I have never restored a database because of a hardware problem. Does anyone else?
No, just Cassandra bug and then user error.
Yeah.
Replication factor 3 hurts. It just goes right out there.
It does everything you ask it to.
Yeah, it's like, oh,
Low latency.
I think that's it.
Wonderful. Well, thank you, everybody.
Yeah.